here for day 9, we just have one quick application of vectors. I'm just going to address this somewhat quickly here and then just give you guys time to practice with this, because really the only way to get good at these is to practice. So it says a ship R sails through a point A in the direction B, and that's a direction vector, and continues past the port P. All right, the port's where the ship might land. All right, so that's down here on the shore. And it says, at what time will the ship be closest to the port? All right. Now, you guys have dealt with this to some degree in other applications, just maybe not with vectors. Okay? Anytime that you are trying to find the shortest distance from a point to a line, you're always going to measure that distance perpendicular to the line. Okay? It's always going to be perpendicular to the line. All right, so what we have here in this case is we have some point, and this is a little bit misleading here because it has R way over there. Okay, what the fact of the matter is you could put R wherever you want on this line. Okay, so I'm going to put R right here at the point that I'm looking for. Does that make sense? That make sense? Okay. Now, what happens is I want to make, if R is where the ship is, I want to look at it at this moment. So the ship is right here, and this is the path that it's traveling along. Okay? I want the shortest distance right there. So what I'm going to do is I'm actually going to look at this in terms of the vectors. I have this direction vector, vector B. Okay, I'm actually going to draw it on the path of the ship. And then I also have this vector to get from the port to the ship. So that's vector PR. Okay. And the key here, as you guys can see, is the fact that if I want it to be perpendicular, then those two vectors are going to have to be what? What was the term that we used for vectors that are at a 90-degree angle? Well, that's for anything at 90 degree, but specifically in vectors. You remember the terminology we used? The vectors are... No, started with an O. Orthogonal. Orthogonal, okay? These would have to be orthogonal. And we said orthogonal vectors, or ones that where the angle is perpendicular, are ones where the dot product equals 0. Okay? The dot product equals 0. So, the key on this, and really the only challenging part of this, is to figure out what is that vector PR. Okay? So let's look at an example here where we actually do this. And by the way, notice, so we're going to do this just in 2 dimensions. Okay? So we have, let's say our ship was moving along this path. So here's our R equals the 1/2 plus t times 3 negative 1. Okay? So my position R is going to be a point. Okay? It's going to be a point. And the x-coordinate, what is the x-coordinate of that point going to be? Think. I have the vector equation of the line. If R is on that line, what is the x-coordinate going to be? What's our x coordinate going to be? 1 plus 3t. That's going to be our x coordinate at any given time. Okay? What's our y coordinate going to be? Yeah, 2 minus t. Okay? So, here's where I've got to figure out a couple of things here. Okay, I defined R as a point. Okay, a point on that line. Okay, now I have point P, and that's 5, negative 1. So if I wanted the vector PR, if I want the vector PR, I have point P, which is 5, negative 1. I have point R up here.
Wait, are P and R vectors or points?
P and R are points. P is the point 5, negative 1. R is a point on this line. Okay. How do we find the vector between 2 points?
Subtract 5 minus 1 plus 3t.
Close.
Or you do 1 plus 3t minus 5.
There we go. It'd be 1 plus 3t minus 5. You always do the coordinate of the point you're going to. So we're going towards R. So I put that coordinate first, and then I subtract the x of the point we're going to, or we're coming from. So it's 1 plus 3t minus 5. And then our y coordinate, or our y component, I should say, would be what?
2 minus t minus negative 1.
2 minus t minus a negative 1. Okay?
So then it would be negative 4 plus 3t.
Okay, yeah, negative 4 plus 3t.
And 3 minus t.
And yes, 3 minus t.
So that's what PR is.
Okay, so that's vector PR. Now, the shortest path from a point to a line is perpendicular to the line. So what direction is the line going? What's our direction vector?
B.
Huh?
B.
It's B. Okay, so what's B in this case?
0.
No.
Oh, wait. That's the...
It's a direction vector.
Yeah.
Negative 1. Sorry, I was slower than I
No, that's a point. On the line. Okay, what's our direction vector on that line?
B.
What is it on this one?
1, 2. Or 3, negative 1.
It's one of those. Which one is it?
1, 2.
2. 2.
This or this?
The first one.
No, the second one.
It's this one, because it's multiplied by the t. Alright?
Yeah.
Come on, guys. We're on like the last lesson of the unit. We should know this one. We should be able to pick this out easily at this point. 3, negative 1 is our velocity vector, okay? So that's the B. Our velocity vector B is 3, negative 1. Now, in order to find the shortest distance, okay, I've got to figure out the time, all right? So I've got to make PR dotted with B equal to 0, because the shortest distance will always be perpendicular to the line, okay? Before we go any further, let's illustrate this, okay? Since it's in 2D, we can graph this pretty easily, all right? So we have the point 5, negative 1. We have the line. It starts at the point 1, 2, and it goes to the right 3 and down 1, according to our velocity vector. So 1, 2, 3, down 1, we're here. 1, 2, 3, down 1, we're right here. So that line is this line right here. Okay? So guys, even just by eyeballing this, this is t equals 0, t equals 1, t equals 2. Just by kind of eyeballing this, I can tell about what my answer ought to be, right? Because that is going to be perpendicular, right? Here's point P. Here's that point R that we defined. Okay? So I'm using this vector here, PR, and I am finding where it is perpendicular to the velocity vector here.
How did you draw it really crap?
How did I draw what?
Did you just guess like, oh, T0, T1, T2?
Well, no, I used the velocity. The velocity said go to the right 3 and down 1. And if I do that once, that's going to be at time 1. If I do it again, that'll be at time 2. Okay?
Which velocity?
The velocity in the line. The 3, -1.
3, -1. Oh.
Yeah, our B. Okay? So here, I'm getting this, and that's really what we're trying to find here, guys, is where is that R, what is that shortest distance? Okay? So to find the shortest distance, I've got to make those perpendicular. That's why I'm doing the dot product equal to 0 here, guys. Okay? So PR is that vector -4 plus 3t. 3 minus t. And B is the vector 3, -1. And I want to make that equal to 0. So now we just have to do the dot product. 3 times a -4 plus 3t minus 1 times 3 minus t has to equal 0. And I can solve this for t. Okay? So -12 plus 9t minus 3 plus t is 0. 10t equals, that's a minus 15, so I'm going to add 15 to the other side. And t equals 1.5. If I look at my graph over here, that makes sense based on what we can see. I know R is going to be somewhere between 1 and 2, where time is 1 and 2. So that makes sense that we got 1.5. The only thing we have to do at this point is make sure that we actually answer the question. All right? So we could do a number of different things. R, if t is 1.5, R is going to be the point 1 plus 4.5, so that's 5.5. And 2 minus 1.5, so there. So that's the point, 5.5, 1/2. Okay. I could give us vector PR. Vector PR is -4 plus 4.5, so that's going to be a 0.5. And 3 minus 1.5 is 1.5. So there's vector PR. But actually neither of those are what the problem asked for. The problem asked for the actual distance. So how do we find that actual distance at this point?
So wait, you just plug in T to the vector?
How do we find the length of a vector? What's another name for that?
Magnitude.
Magnitude, okay? So if I need to know the length of PR, I need to find the magnitude. Okay, so square root of 0.5 squared plus 1.5 squared. So that's 0.25 plus 1.25. So I have the square root of 1.5. Okay? If you want to get that exactly, it's the square root of 3/2, which is the square root of 3 over square root of 2. So I multiply by root 2 over root 2, and I get root 6 over 2. That would be the exact value. Okay?
So the distance of the line is just radical 1.5.
The square root of 1.5, which is square root of 6 over 2. Okay? So there's our answer, or there's our answer.